It's Mrs. Mafucci. Let's continue our discussion of acid-base theory. Let's review the Arrhenius theory first. According to Arrhenius, an acid is anything that produces hydrogen ion in water. When HCl dissolves in water, it produces that hydrogen ion, characteristic of all Arrhenius acids, and the chloride ion. According to the Arrhenius theory, a base is anything that produces the hydroxide ion in water. That's why NaOH is an Arrhenius base. When it dissolves in water, it produces the sodium ion and the characteristic hydroxide ion that all Arrhenius bases produce in water. There's another theory about acids and bases that you need to know, the Broasted-Lowry Theory. But why is there another acid-base theory? That's because Arrhenius theory applies only to those things dissolved in water. The Broasted-Lowry theory can be substances in any solvent. According to the Broasted-Lowry theory, an acid is anything that donates a proton. A proton is essentially a hydrogen ion. According to the Broasted-Lowry theory, a base is anything that accepts a proton, anything that accepts a hydrogen ion. In other words, in the Broasted-Lowry theory, acids are proton donors and bases are proton acceptors. A proton is really just a hydrogen atom that has lost its electron. Remember, the atomic number of hydrogen is 1. That means it has 1 proton in the nucleus and 1 electron. Now, if that hydrogen atom loses its 1 electron, all you're left with is a single proton. The hydrogen ion is a proton. Well, now let's look at this equation that shows Broasted-Lowry theory. Ammonia, NH3, plus water in equilibrium with the ammonium ion, NH4 positive, and the hydroxide ion. In order to understand an equation involving Broasted-Lowry acids and bases, what you want to do is connect with arrows the things that look alike on opposite sides of the equation. For example, doesn't ammonia look like ammonium? And doesn't water look like hydroxide? In order for ammonia to change into ammonium, that NH3 needs to gain a hydrogen ion. NH3 needs to accept a proton. That's why NH3 is a base. Bases on one side of the equilibrium equation turn into conjugate acids on the other side. Now let's look at water, H2O. In order for water to change into the hydroxide ion, water must lose a hydrogen. It must lose a proton. That means in this equation, water is acting like a Broasted-Lowry acid, which means on the opposite side, the OH negative ion, the hydroxide ion, it is the conjugate base of water. Let's consider another example. Fluoride plus HCl in equilibrium with HF and the chloride ion. Remember, the first step is to connect substances on opposite sides of the equilibrium that look the most alike. So we're going to connect fluoride and HF and HCl and Cl negative. Well, now it's time to analyze the equation. In order for fluoride to change into HF, doesn't it have to accept a hydrogen ion? Doesn't it have to absorb a proton? That means fluoride is a base. Fluoride gains a hydrogen ion to change into HF. Now let's look at what HCl does. In order for HCl to change into the chloride ion, it must lose a hydrogen. It must lose a proton. That means HCl is a Broasted-Lowry acid. F negative, HF, is a conjugate acid-base pair. HCl and Cl negative is another conjugate acid-base pair. Strong acids have weak conjugate base pairs, and weak acids have strong conjugate acid-base pairs. So when you get an equation, you're going to have to identify the Broasted-Lowry acids and bases, and then tell me the relative strengths of each. You're going to go to Table M to check for the strengths of acids and bases. Look at HCl on Table M. Doesn't it have a large Ka? It's a strong acid. When HCl donates its proton and becomes the Cl negative, the chloride is a weak base. Strong acid on the left becomes a weak base on the right. Well, now, HF is one of the products. Find HF, hydrofluoric acid, on Table M. Do you notice that hydrofluoric acid is a weak acid? It has a small Ka. That means it was formed from a strong base. The fluoride ion is a very strong base. It's important to note that you don't have to have strong acids and strong bases on the same side of the arrow, or weak acids and weak bases on the same side of the arrow. Sometimes you can have a strong base and a weak acid, or a weak base and a strong acid. Let's look at two more examples. Step 1, connect the things that are changing. HCl becomes the Cl negative ion. The OH ion becomes the water molecule. In order for OH to become water, it must gain a proton. That means the OH negative ion, the hydroxide ion, is a base, which means water, on the other side of the arrow, is its conjugate acid. If you look up water on Table M, water is a weak acid with a small Ka. Since water is a weak acid, the hydroxide ion must be a strong base. Now consider HCl and the chloride ion. HCl is a strong acid with a large Ka. That means when it loses its proton, its hydrogen ion, it changes into a weak conjugate base. Let's look at another example. Step 1, connect the things that are changing. For water to become the hydronium ion, it must gain a hydrogen. It must gain a proton. Therefore, it's a base. It should make sense to you that water is a weak anything. A weak acid, a weak base. That means the hydronium ion on the opposite side of the equilibrium arrow is a strong acid. Sulfuric acid, H2SO4. According to Table M, it's a strong acid, which means when it loses its proton, its hydrogen ion, and changes into the HSO4 ion, that hydrogen sulfate ion is a weak base. Look at these conjugate acid-base pairs. Well, how does a conjugate acid-base pair differ? HCl and Cl negative, don't they differ by one hydrogen ion? Acetic acid and the acetate ion, they also differ by only one hydrogen ion. NH4 and NH3, one hydrogen ion. And lastly, HNO3 and NO3 negative, don't they differ by one hydrogen ion? Conjugate acid-base pairs differ by one hydrogen ion, by one proton. It should make sense to you that the Broasted-Lowry acid will be the substance of the conjugate pair that has the most hydrogens. HCl and Cl negative. HCl is the acid. It has one more hydrogen. HCl has one hydrogen. The chloride ion has none. Now let's consider water. Water can function as both an acid or a base according to Broasted-Lowry theory. Let's write the reactions of water with the hydrogen carbonate ion, in which water acts like an acid and acts like a base. In this situation, H2O, doesn't it change into the hydroxide ion? That means in this first example, water is acting like an acid. In the next example, look at water. To change from H2O to H3O positive on the opposite side, doesn't it have to gain a proton to become the hydronium ion? That means in the bottom example, water is gaining a hydrogen to become the hydronium ion. It is a Broasted-Lowry base.